a weak acid or a weak base with a certain pKa, and I look it up in tables, and if I use, for example, this system here, let's see, H2CO3 as by itself, and I put its conjugate, that's the acid, I put its conjugate base, would be HCO3 minus in case, I put this in equal amounts together, then I have a pH buffer around pH 6. It goes from 6.1 to 7.1 up and to 5.1 down. It buffers that region. The same with your acetic acid. If I mix this with 50% of acetate, just that I have an equal amount of HAC and AC minus, I put, for example, either acid in there, that makes the sodium, the acetate, the AC minus, or I put it in as a salt, sodium acetate, and then I have a pH buffer of 4.75. It goes from 3.75 to 5.75. Okay, this is how you find how to make your buffer. There are many, many other buffer systems. And now I'm asking you a question. So a buffer is its conjugate its conjugate acid, ACE here, its conjugate acid combined with an equal amount. Let's say that again. A buffer is a weak acid combined with its conjugate base in the same concentration. Okay? So, and vice versa, a buffer is a weak base combined with its conjugate acid at the same concentration. So now I will have an ammonia solution, and I want to make a basic buffer. Ammonia, you need to know, is probably an acid or base. By now we should know that, but it says right here. So you have ammonia, and you want to make a buffer. Would you add sodium hydroxide? Would you add sodium chloride? Or would you add HCl to the ammonia to make a basic buffer? So obviously this picture will tell you a little bit about this here, and just give it a stare, please. You want to make the conjugate form of it. First of all, you need to see, is this a base or is this an acid? Okay? It says right there. And we had these questions before, many times before. We determined that NH3 was something specific. What was it? Okay. Okay. The answer is right here. Right there. Okay? So how do we get from here to there? How do you get from here to there? What do you have to do? What do you have to react with each other? I think that's about as much as I can tell you. Or you look at that equation here, for example. All right? So how do you get from here to here when you add something, one of these things here? You add this here, would you get there? Would you get there? Or would you get with this there? Don't use that equation, just use the product, the reactant and the product here. Okay, discuss it with each other, please. So there are two ways of making a buffer. One is you add enough acid or you add enough base that you form its conjugate base or acid. Or the other way, you add a salt which has already the base or the acid in it. And let's think about this one more time. Give me your solution, please. Discuss it with each other. You need a strong? Yes. What is it? Yeah, we're getting there. Okay. So this is a base here. That's a base. It wants to take protons from somebody. But it's not a strong base, but you have a very strong acid. That's a very strong acid. I said, I don't want that proton. Okay, I don't want it. You can have it. Okay. So they said, okay, the NH3 says, I'll give me that proton. I will form NH4 plus, and I do put enough HCl in there till I have this in equal concentration, and with this I have my buffer. So what would be the pH of such a buffer here? So if you look at this here, for example, this would be the one that would be the base constant, and this would be the acid constant, isn't that? That would be the acid constant. So I take pKa times the log of the concentration of NH. What was it? AC over. 1 second. The log of HAC over AC over HAC, HAC over AC minus over AC plus, so that's the conjugate base over the acid. Yeah, all right. So, and with this you can calculate it. This is your Ka, and there was your equation. There was your equation. Where's my Henderson Hasselhoff here? It's not here. Okay. So pH is pKa plus log of the form of the acid, the base form divided by the acid form. Okay. Base form divided by the acid form, and so you know what would be the pH around where it would buffer. It would be around 9.3. Okay, because this is your Ka for that system. All right. So that was very successful. Did I show this already? The result? Yeah, I did. Yeah. No, I didn't. Well, let's see it again. Yeah, I did. It's green already. Okay. Play with your professor. All right. So what we have here, we have NH3 plus, and we need H3O plus gives NHO4. Okay, that's HCl gives an H3O plus and HCl minus. This is your conjugate acid. That's the initial base. So that forms the buffer, and this was your answer. Now, we have in yellow here is the titration of nitric acid, and I tell you nitric acid is a strong acid. HNO3 is a strong acid. And I titrate this with a strong base, which you did in the lab. So this is the yellow line here. This is obviously the yellow line. This is the same. And now I dilute this whole solution by a factor of 10. I put 10 times more water in there, okay? And I dilute this. Now I want to know from you, would the new titration curve in green would look like this, would look like this, or would look like this? Why don't you think about this a little bit, or a lot, and try to answer this? So there are 3 points that you need to consider, even in a strong acid, if you compare them with each other. What was the answer? C? Okay. I think you should think a little bit more. All right. C is your answer. But it's nice and warm here. So let's have a look at this here. And it doesn't rain. It doesn't rain. Okay. Okay. Alrighty. So you need my thinking about this. Okay. Now you have a strong acid. And that strong acid dissociates. Okay. It completely dissociates. So you have a fixed amount of H3O plus. Moles, not moles per liter. You have a fixed amount of H3O plus. Now you put these moles in a certain volume, then you can calculate how many moles per liter you have. Okay. So that will give you your initial pH. Now that means you have now the H3O plus. You haven't changed the moles. You haven't changed at all the H3O plus. But you have changed your volume. So your moles per liter will be smaller if you have a larger volume or larger. The moles per liter will be smaller. So and this is your concentration of H3O plus, isn't that right? So what will your pH be? Will be higher. Exactly. That's the first thing. So we are talking about the green line, so this doesn't help. Okay, it's all higher. All right. Now the next thing is you have a fixed amount of HNO3 in there, and the fixed amount was a certain molarity of HNO3. And if you neutralize this with OH minus, you have to take one atom or one molecule of H3O plus and neutralize it with one molecule of OH minus to make water. Okay, H2O. Now you could have this in a bathtub, or you could have this in a small jar. If you have the same amount of H3O plus in there, amount, not molarity, moles, that's the amount, not molarity. If you have the same amount, would that equivalence point change? No. Now you come to the end, and you have 0.1 molar sodium hydroxide. That's what you're adding. Before, you just had your curve there. It was whatever you put in there got flat because you just were adding OH minus. But now you have a whole lot more solution, water, and you're adding your 0.1 molar sodium hydroxide in this. Would the concentration of the sodium hydroxide in that new solution, would it be higher or lower? You're diluting it, isn't it right? So the concentration would be lower. What would happen to the pH? The pOH would be lower, and the pH, would that be true? Would be higher? I don't think so. It would not be higher. Because what was our initial curve? Initial curve, what color was it? Yellow? So it must be, why don't you think about this? All right? So we are close, but no cigar yet. But if you listen carefully, you can solve it already. So you're diluting at the end, you're diluting your OH that you add in there. So it will be more dilute than if you have the undiluted solution. Okay, let's have a look at this. We're talking about the strong acid, isn't it right? Yeah, we're talking still about the strong acid. Yes, that's very good. Because the equivalence point is the same. Okay, you just neutralize atom by atom or molecule by molecule H3O plus with OH minus, and this should not change. Even if you dilute it, you will have the same number of molecules of H3O plus in there. And with this, your solution is, you have, first of all, you diluted it by 10. It was 1 pH unit. Okay, that was clear. And then the equivalence point is unchanged. All right, this is fine too. And then the third thing is you diluted it by 10, so it goes down by 1 pH unit. If you dilute a 0.1 molar sodium hydroxide solution by 10, because that's what you do essentially, you add it to a much more volume, so you go down by 1 pH unit. And this was the right answer. Now we come to the kicker. Okay, we're dealing now, and this is a very difficult issue. We're dealing with acetic acid, and this is a weak acid. And this is the line in yellow. This is our acetic acid titration with a strong base, and the base is potassium hydroxide, KOH, so it's OH minus, completely dissociated. And you get these curves, and you see there is these. Let's have a look at this. It's also pretty drawn out. It shouldn't be quite as long. You see there should be a long, or there is a long buffer region here. You see that's your buffer region. So you dilute this now by a factor of 10. So what happens here to your initial pH? What happens to your equivalence point? And what happens to your final pH? Please think about it and see if you can crack the conundrum here. And if you can crack it, you got it all down pat. You also need to think about, if you just think about what I said about dilution in the buffer region, then you can solve it without knowing anything else. Not bad for some of you. Okay, let's talk a little bit about this. So at the beginning, you diluted by a factor of 10, so the pH goes down by 1 unit, is that right? But now you have a weak acid. What happens if you dilute this here? You put a lot of water in here. What happens? You push it to which direction? To this direction. So would the pH be the same as you would dilute a strong acid, or would the pH be lower or higher than compared to the strong acid? So that, yeah, okay. So if you can answer this, there's maybe one of them might have it here. Would it be a whole unit higher? No, it would be not a whole unit higher. And then your acetic acid, or your weak acid, you have a certain amount, and this whole amount needs to be all dissociated till you have all the, if you add OH minus here, you add OH minus, you take this away, and so now the equilibrium is disturbed, you're now making more H3O plus, okay? So you keep this until you have your equilibrium point, and there the equilibrium point will be probably the same than the equilibrium point. I don't know. Never mind. Okay, let's discuss this with each other, please, in the last minute, and then we talk about this more the next time. But this is important that you understand it. It's not easy. I understand. I give you that. Not easy. Let's see what the result is. We're in the last minute here, and so you can think about this till Friday. So I'll see you on Friday, and don't forget to pick up your Scantrons upstairs. They are now till 3 o'clock. They are there. Hmm?